Welcome to this problem-solving session. Today, we'll dive into problem number 1040, titled Moving Stones Until Consecutive 2. In this problem, we'll explore how to strategize and optimize the process of moving stones to achieve consecutive placement. Let's get started. In this problem, we are tasked with rearranging stones on a number line so that they form a consecutive sequence. You're given an array called stones, where each element represents the position of a stone, and these positions are sorted in increasing order. The catch is that you can move any stone to a new, unoccupied position between the smallest and largest numbers in the array, inclusive. The ultimate goal is to make the stones consecutive, meaning each adjacent stone has a difference of exactly 1. The output of the problem will be an array of two values, the minimum number of moves required to achieve this consecutive arrangement, and the maximum number of moves that could be needed. Let's examine some examples to understand this better. In the first example, the input array is stones equals 7, 4, 9. The output is 1, 2. For the minimum moves, we can move the stone currently at position 4 to position 8. This makes the array 7, 8, 9, which is now consecutive, requiring only one move. For the maximum moves, we can first move the stone at position 7 to position 5, and then the stone at position 9 to position 6. This transforms the array into 4, 5, 6, which is also consecutive, but this process requires two moves. Another example has stones equals 6, 5, 4, 3, 10. Here, the output is 2, 3. For the minimum moves, we can move the stone at position 10 to position 2, and the stone at position 6 to position 7. This results in 3, 4, 5, 6, 7, which is consecutive and takes two moves. Now let's look at the maximum moves for this case. To achieve the maximum moves for stones equals 6, 5, 4, 3, 10, we can move the stone at position 10 to position 7. Then, we move the stone at position 3 to position 8, and finally the stone at position 4 to position 9. This results in the array 5, 6, 7, 8, 9, which is consecutive, and this process takes three moves. In the third example, the input is stones equals 100, 101, 104, 102, 103. Here, the output is 0, 0, because the stones are already arranged consecutively. The difference between each adjacent stone is already 1, so no moves are required at all. This demonstrates that in some cases, the stones may already satisfy the condition without any rearrangement. Now, let's consider some edge cases and constraints to keep in mind. There are a few edge cases we need to consider for this problem. First, if the stones are already consecutive, such as stones equals 1, 2, 3, then both the minimum and maximum moves will naturally be 0 since no rearrangement is necessary. Another case involves large gaps in the stone positions, such as stones equals 1, 1000, 1 million. Here, the solution must handle situations where multiple intermediate positions need to be filled, particularly when calculating the maximum moves. Finally, given the constraint that the array can have up to 10,000 elements, the algorithm must be efficient, ideally running in linear or near linear time. This ensures it can handle the upper limits of the input size without exceeding runtime constraints. To solve this problem, we first considered a brute force approach. The intuition behind this method is quite straightforward: simulate all possible moves for each stone to determine the minimum and maximum moves needed to make the stones consecutive. The steps involve generating all permutations of the stone positions, calculating the moves required for each configuration, and then tracking the minimum and maximum moves across all cases. However, while this approach is conceptually simple, it is computationally expensive. Since generating permutations has a factorial time complexity of O(n), this method becomes impractical for larger arrays. This inefficiency is the key limitation of the brute force approach, making it unsuitable for solving the problem efficiently at scale. Instead of brute force, we can take advantage of the fact that the stones' positions are sorted, which leads us to the sliding window approach. The intuition here is to focus on subsets of consecutive stones, avoiding the need to generate all permutations. The key observations are that the minimum moves depend on how many stones are already in a consecutive range, and the maximum moves involve filling the largest gaps one stone at a time. By sorting the stones array, we can use a sliding window to efficiently determine the largest group of consecutive stones. From there, the minimum moves can be calculated as the total number of stones minus the maximum stones in a valid window, while the maximum moves are determined by analyzing the largest gaps. The sliding window approach reduces the time complexity to O(n), making it significantly more efficient than brute force, and it also requires minimal extra space. Building on the sliding window approach, we can further optimize it using a two-pointer technique. This optimization allows us to dynamically adjust the window size and reduce redundant computations. The process starts by using two pointers to define the bounds of the window. The right pointer expands the window as long as the gap remains within an allowable size, while the left pointer adjusts to maintain a valid window when necessary. By maintaining this dynamic window, we can efficiently calculate both minimum and maximum moves based on the principles outlined earlier. Like the sliding window method, this approach also has a linear time complexity of O(n) and requires constant space, but it offers a more dynamic way to handle the problem, ensuring that no unnecessary computations are performed. After evaluating the different approaches, we chose the sliding window strategy as the most practical solution. This method strikes a balance between simplicity and efficiency, avoiding the computational overhead of brute force while being straightforward to implement. Although the two-pointer optimization is a slight enhancement, it does not provide a significant performance gain for typical inputs, making the sliding window approach the preferred choice. The key advantages of this strategy include its linear time complexity, which ensures scalability for large inputs, and its ability to leverage the sorted property of the input to eliminate unnecessary computations. However, it does require familiarity with sliding window patterns, which might be less intuitive for beginners. In contrast, the brute force approach was rejected due to its infeasibility for larger inputs, and the two-pointer optimization was deemed unnecessary for most practical scenarios. By adopting the sliding window approach, we achieve an optimal combination of performance and simplicity, making it the most effective strategy for solving this problem. This method allows us to efficiently determine the minimum and maximum moves required to make the stones consecutive, ensuring that the solution is both scalable and easy to understand. Its balance of computational efficiency and conceptual clarity makes it the ideal choice for tackling this challenge. In this problem, we need to determine the minimum and maximum number of moves required to make a sequence of stones consecutive. The stones are placed on a one-dimensional number line, and each move allows you to shift one stone to any unoccupied position. The ultimate goal is to rearrange all the stones so that their positions form a consecutive sequence. To approach this, we start by considering a brute force solution. The intuition here is to simulate every possible move for the stones, testing all configurations to determine both the minimum and maximum moves necessary. First, we parse the input. Let the array stones represent the positions of these stones. By sorting the array in ascending order, we simplify the process of identifying and analyzing the gaps between consecutive stones, which is critical for the subsequent calculations. Next, we calculate the maximum number of moves required. This value is determined by filling the largest gaps between the stones. If there are n stones in total and the largest gap between two stones is g, the maximum moves can be calculated as g n1. This is because we aim to fill the gap while maintaining consecutiveness. For the minimum moves, the strategy is slightly different. Here, we focus on how close the stones already are to forming a consecutive sequence. Using a sliding window of size n, we identify the smallest range that contains all n stones. The number of moves required is equal to n number of stones already in the window, since we only need to reposition the stones that fall outside this range. To refine the solution, we iterate over all configurations, simulating moves for each stone to minimize the largest gap. This step ensures we capture the smallest number of moves required across all possible positions. Finally, we handle edge cases, such as situations where the stones are already consecutive, which means both the minimum and maximum moves are 0. Similarly, if there are only two stones, the moves are always exactly 1, regardless of their positions. Once these calculations are complete, we return the minimum and maximum moves as a tuple, min_moves, max_moves. To better understand this process, let's walk through an example. Consider the input stones equals 6, 5, 1, 9. The first step is to sort the stones, resulting in 1, 5, 6, 9. Next, we calculate the largest gaps between consecutive stones. For this example, the gaps are 4 between 1 and 5, 1 between 5 and 6, and 3 between 6 and 9. To determine the maximum moves, we use the formula 4 plus 3, 4 to 1, which gives 6. For the minimum moves, we use a sliding window approach. By moving 1 to 4 and 9 to 7, we can achieve a consecutive sequence, requiring only 2 moves. Therefore, the result for this example is min_moves, max_moves equals 2, 6. From this analysis, several key insights emerge. Sorting the stones simplifies the calculation of gaps, as these gaps are directly between consecutive elements in the sorted array. The sliding window technique is efficient for finding the smallest range that includes all the stones, which is crucial for determining the minimum moves. We also see that large gaps dominate the calculation of maximum moves, while small adjustments dominate the calculation of minimum moves. Special edge cases, such as stones that are already consecutive or configurations with only 2 stones, require tailored handling to avoid unnecessary computations. For the data structures, we primarily use an array to store the stone positions, a sliding window to efficiently identify the smallest range, and variables to track the gaps and the move counts. Analyzing the algorithm's complexity, the time complexity is dominated by the sorting step, which takes n log n. The subsequent calculations, including gap analysis and sliding window operations, are linear, resulting in an overall time complexity of n log n. The space complexity is O(1), as the computations are performed in place without requiring additional data structures. To solve the problem of determining the minimum and maximum number of moves required to arrange stones into consecutive positions, we break the problem into 2 parts, computing the maximum moves and the minimum moves. ###explanation. 1. Sorting the stones. The first step is sorting the positions of the stones. This helps in determining the range of the stones and simplifies the computation of gaps. 2. Maximum moves. To compute the maximum moves, we use the given formula. Subtract the number of stones, n, from the range of the stones, stones-1, stones, 0, then adjust for the smallest gap on either end, min, stones, 1, stones, 0, stones-1, stones-2. This ensures that we maximize the movement while maintaining the constraints. 3. Minimum moves. For the minimum moves, we use a sliding window approach. The idea is to find the smallest window of stones that can be made consecutive with the least number of moves. We maintain a window, I, j, where the number of stones in the window is at most n. If the window size is n1 and has 1 gap left, the minimum moves can be adjusted to 2. Otherwise, the moves required are calculated as n stones_n_window. 4. Sliding window logic. We iterate over each stone position as the start of the window, I. For each I, we extend the window, j, as long as the gap, stones, j, stones, I, plus 1, is within the limit of n. This ensures that we consider all valid windows and compute the minimum number of moves required for each. Finally, we return both the min_moves and max_moves as a list. This solution efficiently calculates the result using sorting and sliding window methods, ensuring optimal performance even for larger inputs. Here, we start by importing the necessary libraries and defining our solution class. Inside the number moves stones II method, the input array stones is sorted to ensure that the stones are analyzed in increasing order of their positions. This helps simplify the calculations for the moves. Next, we calculate the maximum number of moves. The formula used determines how many positions would need to be filled to make all stones consecutive, subtracting the number of stones already present. We also account for edge cases by subtracting the smaller gap between the first 2 stones and the last 2 stones. This ensures that the maximum number of moves is calculated accurately for any configuration of stones. Then, we move on to the minimum number of moves, which is determined using a sliding window technique. The idea here is to find the smallest window in which the stones can be rearranged to become consecutive, minimizing the moves required. We initialize min moves to the maximum possible value and use 2 pointers, I and j, to iterate through the sorted stones array. For each stone at index I, we expand the window by incrementing j as long as the difference between stones, j, and stones, I, plus 1 is less than or equal to the total number of stones. Within this window, we calculate the number of stones and check if it matches specific conditions, such as leaving exactly one stone outside the range. If it does, we update min moves to 2, as only 2 moves are needed in such cases. Otherwise, we minimize min moves based on the gap outside the window. Finally, we return an array containing min moves and max moves, representing the minimum and maximum moves required to make the stones consecutive. This concludes the implementation. To solve this problem, we start with the given array of stones 6, 5, 4, 3, 10. The first step is to sort the stones so that we can work with them in increasing order. After sorting, the array becomes 3, 4, 5, 6, 10. Now, we calculate the maximum moves required to make the stones consecutive. The formula for this is max_moves equals stones, dash 1, stones, 0, and plus 2 min, stones, 1, stones, 0, stones, dash 1, stones, dash 2. Breaking this down, the gap between the first and last stone is 10, 3 equals 7, the number of stones is 5, and the smallest gap on either end is the minimum of 1, from 4, 3, and 4, from 10, 6. Substituting these values, the calculation becomes 7, 5 plus 2, 1 equals 3. So, the maximum number of moves needed is 3. With the maximum moves calculated as 3, we now focus on finding the minimum moves. To do this, we use a sliding window approach. We initialize min_moves to infinity and iterate through the stones with 2 pointers, I and j, to define a window. Inside this window, we check how many stones are already consecutive and how many moves are needed to fill any gaps. For the first window, where I equals 0 and j moves up to 4, we calculate the window size as stones, j, stones, I, plus 1, which is 6, 3 plus 1 equals 4. This is a valid window since it includes up to 4 stones. The number of moves needed is n stones_n_window equals 5, 4 equals 1. This updates min_moves to 1. Sliding the window further, such as by incrementing I to shift the range, doesn't improve the result. Therefore, the final values are min_moves equals 1 and max_moves equals 3. The output for this example is 1, 3. Now let's look at a second example with the stones 1, 2, 3, 4, 100. First, we sort the array, which remains 1, 2, 3, 4, 100. To calculate the maximum moves, we use the same formula as before, max_moves equals stones, dash 1, stones, 0, and plus 2 min, stones, 1, stones, 0, stones, dash 1, stones, dash 2. Here, the gap between the first and last stones is 100, 1 equals 99, the number of stones is 5, and the smallest gap on either end is the minimum of 1, from 2, 1, and 96, from 104. Substituting these values, the calculation becomes 99, 5 plus 2, 1 equals 95. So, the maximum number of moves is 95. Next, we calculate the minimum moves using the sliding window approach. For the first window, where I equals 0 and j moves to 4, the window size is stones, j, stones, I, plus 1, which is 4, 1 plus 1 equals 4. This means 4 stones are already consecutive, leaving 5, 4 equals 1 move needed to make the sequence fully consecutive. As we slide the window further to include other subsets of stones, we find that no better result is achieved, confirming that min_moves equals 2. This happens because the large gap between 4 and 100 limits the ability to reduce the number of moves further. Therefore, for this example, the final values are min_moves equals 2 and max_moves equals 95. The output here is 2, 95. Now, let's move to a third example with the stones 7, 4, 9, 1, 10. After sorting, the array becomes 1, 4, 7, 9, 10. For the maximum moves, we calculate the gap between the first and last stones as 10, 1 equals 9, the number of stones is 5, and the smallest gap on either end is the minimum of 3, from 4, 1, and 1, from 10, 9. Substituting these values into the formula gives 9, 5 plus 2, 1 equals 5. So, the maximum number of moves is 5. For the minimum moves in this example, we again use the sliding window approach. By calculating the window size and the number of stones inside each window, we determine how many moves are needed to make all stones consecutive. The sliding window mechanics reveal that the best result is achieved with min_moves equals 2. This is possible because the gaps between stones are more evenly distributed compared to the previous example. Therefore, for this example, the final values are min_moves equals 2 and max_moves equals 5. The output is 2, 5. In this problem, the time complexity is driven by two main calculations: the maximum number of moves and the minimum number of moves. For the maximum moves calculation, the first step is sorting the stones array. Sorting is the most time-intensive part of this step, taking O, n asterisk log, n, time, where n is the number of stones. Once sorted, we perform a constant time calculation involving the range of the stones and some adjustments to determine the maximum moves, which runs in O, 1. Thus, the overall complexity for this part is O, n asterisk log, n, dominated by the sorting step. Now, for the minimum moves calculation, we use a sliding window approach. Here, two pointers, I and j, are used to iterate through the stones array. The outer loop runs once for each stone, which takes O, n, and the inner loop adjusts j to maintain the condition that the window size is valid. Since j only moves forward across the array, it increments at most n times in total. Any operations inside the loop, including updating variables like min_moves or stones_n_window, run in constant time, O, 1. This makes the overall time complexity of the sliding window process O, n. When combining both parts, the overall time complexity includes the sorting step, which is O, n asterisk log, n, and the sliding window process, which is O, n. Since O, n asterisk log, n, dominates O, n, the total time complexity for the solution is O, n asterisk log, n. Now looking at the space complexity, sorting generally requires additional memory. For in-place sorting algorithms, this space requirement is O, n. Aside from sorting, the solution uses auxiliary variables like max_moves, min_moves, j, and stones_in_window, all of which take constant space, O, 1. No additional data structures are used, so the total space complexity is determined by the sorting step, resulting in O, n. To understand the efficiency of the optimized approach, let's compare it to a brute force solution. In a naive approach, we would calculate both the minimum and maximum moves by evaluating all possible configurations of the stones. This would involve generating and checking all permutations or combinations, leading to a time complexity of O, n. Factorial time, which grows extremely quickly as n increases. The space complexity of brute force would be O, n, accounting for the recursion stack or storage of intermediate states. In contrast, the optimized approach achieves significant improvements. The time complexity is reduced to O, n asterisk log, n, as sorting dominates the computation, and the sliding window contributes only a linear pass. The space complexity remains O, n, but without the overhead of storing intermediate states. Finally, we can mathematically prove the big O notation of the optimized approach. Sorting the array is the most expensive operation, with a complexity of O, n asterisk log, n. The sliding window adds O, n, but does not change the overall complexity. When combining the two, O, n asterisk log, n, remains the dominant term. Space usage is limited to the sorting process, which is O, n, making the solution efficient in both time and space. When working on problems like moving stones until consecutive 2, there are a few common pitfalls to be aware of. First, forgetting to sort the input can cause significant issues. Many solutions rely on the assumption that the stones or elements are in order, so failing to sort means gaps or overlaps might not be accounted for correctly. For example, if stones are given as 4, 1, 7, and you don't sort them, calculations for gaps between stones will be meaningless. Next, edge cases are often overlooked. Arrays with only 2 or 3 elements, or inputs where the stones are already consecutive, need special attention. For instance, if the input is 1, 2, 3, the solution should immediately recognize that no moves are required. Another mistake is relying on a brute force approach. While it might work for small inputs, it's not scalable and will likely run into performance issues for larger constraints, such as when the input size is up to 10,000. Finally, off-by-one errors are a frequent source of incorrect results. These errors often occur when calculating gaps, such as incorrectly computing the gap between stones, 1, 4, as 4, 1 equals 3 instead of subtracting an additional 1 to account for the stones themselves, resulting in 4, 1, 1 equals 2. Another challenge in solving these problems is accounting for multiple valid states. In scenarios where there are several possible configurations, such as moving stones to different positions, it's crucial to account for all valid options to avoid partial solutions. Now, let's focus on some key insights for interviews. First, remember that problems involving making elements consecutive often boil down to sorting the input and analyzing the gaps between elements. Sorting provides a clear, linear view of the problem, making it easier to reason about. Second, it's important to consider both the minimum and maximum moves. For minimum moves, the goal is typically to find the smallest valid sequence, whereas for maximum moves, you're looking to fill the largest gaps. Efficiency is another major point. Interviewers expect you to move beyond brute force approaches quickly, as these are rarely acceptable. Lastly, always be prepared to discuss edge cases. For example, you might be asked how your solution behaves when the input is already consecutive or when the input size is very small. Being able to articulate these scenarios clearly can make a strong impression. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 128, longest consecutive sequence, also deals with making elements consecutive, while LeetCode 945, minimum increment to make array unique, involves transforming elements with minimal moves. Similarly, LeetCode 670, maximum swap, and LeetCode 164, maximum gap, both touch on reordering or analyzing gaps in arrays. These problems share conceptual similarities and are excellent practice to build your intuition. Additionally, there are alternative approaches you can use to solve this type of problem. A sliding window technique, for example, is highly efficient for finding the minimum moves, as it allows you to determine the smallest range that can contain all stones consecutively in O(n) time. However, implementing it requires careful handling to avoid off-by-one errors. For maximum moves, a greedy approach works well. By iteratively filling the largest gaps, you can achieve a straightforward solution, though it might not be immediately intuitive to some. Finally, applying a mathematical analysis of gaps can lead to even faster solutions. By directly analyzing the sum of gaps or other mathematical properties, you can sometimes derive an elegant approach. However, this method often requires a deeper understanding of the problem's structure, which may take additional time to develop. Great work! To wrap up, we reviewed the main points of the problem moving stones until consecutive 2 and the approaches to solve it. Remember the key takeaways about efficiency and edge case handling. Thanks for watching, and don't forget to like and subscribe for more coding content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!